Yo, 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 what's up, everybody? Welcome back. Today I want to work on some memory allocators in Zig. So, a while back, we kind of wrote this whole allocator system. The intent here was to stop working with like individual allocations, but kind of more like chunks of allocations. The thought there was that if you wanted to make sure that you were handling all of your error cases correctly, it's actually kind of easier if your error case is like handling is the same as your typical handling. And so like if you allocate in batches, it means that you don't have to do that shit where you're like, maybe it's a bit easier to show here, where you're like, I have some function do stuff. Maybe I'll get some syntax happening working here. Function do stuff, and he, can fail. And here I do something where he takes in like an allocator, right? And he does like, let me allocate some stuff, and I'm gonna maybe like return that stuff. Let me return that shit. So I'm gonna be like alloc some stuff, 1,000 bytes of stuff, and then do something, and then return ret, right? Do stuff. Now, if this was like to fail, now all of a sudden this leaks because you didn't actually return it. So now you have to do like error if we fail, like free this stuff, right? And so this kind of is like suboptimal because there's a lot of like potential for you to fuck this up, and you probably don't ever run it, right? Because in reality, your error cases are typically not that frequent, right? So what we do instead, the memory management scheme we've kind of settled on is instead we just do this. We write leaky here. We just don't free, right? And we don't track this thing. And what we do instead is we have like in main, we have like we do this thing where we say like we have a scratch allocator. Scratch alloc, something. We'll ignore the details here. And what we say is, every once in a while, if we're gonna like do some stuff, we might say like, let's checkpoint the allocator, and then we'll call do stuff, and we'll say go for it, do whatever you want, right? So we like feed him like your allocator, and then later we just say scratch restore checkpoint, right? Now, as long as like we don't let anything from this leak out, like we do like this is that, and we like use this thing here, we do whatever we want. As long as like this doesn't leak out of this scope, it's totally fine. It's kind of just like a stack that you can like inject. Sorry, I'm gonna sneeze. Maybe? No? God damn it, dude. Oh, that's the worst. So this is kind of like the scheme that we use frequently. The problem with this scheme is, say I want to use like a hash map in here, right? To do some like counting or something, right? So we say like let's alloc a hash map, and we have to use like the same allocator here. And now what happens is like this hash map is not like something that we are returning to the caller. In reality, at the end of this function, the hash map memory could be like completely reclaimed. But since we don't ever like, we can do this, right? Like dinit this thing, and idealistically, he would like clean up the memory. However, implementation details of our scratch allocator make this not possible, right? Because what we do is, in order to make this checkpoint thing work correctly, the easiest thing that we can do here is just like, can I zoom in? Is make a chunk of memory. This is like a big buffer. We have like an arrow somewhere that points to like where we are in memory. And all we do when we allocate is we just like bump the arrow. We bump the arrow down, right? And as boom, 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 boom. And then when we like restore the checkpoint, we just like reset it to where it was before, right? Easy, easy, easy. But that means that if the hash map, like we'll like allocate the memory for our return, boom, and we'll like put our stuff in there, and then we'll allocate a hash map here, right? And this stuff goes here, and we can't like, we could like write down this location, right? So you could solve this part by like passing in the scratch allocator here, right? And then doing like a checkpoint here, right? Defer checkpoint, scratch, restore, checkpoint. Now we're kind of chilling, right? As long as everything that goes in this return is like not allocated. But what if you have like a list of strings that you're returning? Now all of a sudden you want to do like more string allocations down here, and that doesn't work so well anymore, right? Because now you have like the array, you're like scratch your like hash map that you don't give a fuck about, but then you have all of this string storage that you actually do have to return. And so what happens is like this whole area gets wasted. And there's not like a simple way around that with like the scheme that we have right now. You could have like free lists or whatever, try to reclaim, but what I think is an easy, simple fix to this problem is if you just allocated from both ends of the buffer. We don't do this right now, but you could make it so that this function takes in like return alloc. You know, you could do like something like this. It's like return alloc and scratch alloc. Scratch alloc, right? And what these could do is you could just then use the return alloc for everything that you want to return. You know, return alloc here and on all of your string allocations down here. And then you use the scratch allocator for your hash map. Like this, everyone's happy. You know? Then all you have to do is you just have to like checkpoint the scratch allocator here and restore it at the end. Hype. And what I'm thinking is if you just have a double-ended buffer here where you can kind of allocate from both sides, kind of like without any real rules on like how you're going to use those things, you can just allocate your return date, your array here, your strings here, and then you can allocate the hash map down here. And then when you're done, just nuke this stuff and then leave this thing kind of like incremented. That's kind of the idea for today, is to implement something that does that, which I think should be relatively easy. But I think this should solve the problem. So I think I want to start by writing a little bit of like a test case for this thing. I think we could come up with a situation where we could maybe like measure, something that has like some loss of memory and then kind of see how much we improve it by doing this thing. So let's get moving. Let's get moving and grooving. I guess we can kind of use this as like some inspiration. So let's do something where we do have like an existing allocator somewhere. We have our scratch alloc in our alloc library. Scratch alloc, that's what we call this guy. And so I guess we can kind of use this. What's maps got to do with hash? Hi. Sometimes you're trying to map things to each other. And you hash them to make the keys. Okay. So I guess let's make our test case use that allocator. So I guess can we where's like a nice place to do this? Maybe in here for now. In our standard library, we'll just make a little test executable. I think that makes sense. So we'll say b add executable, and we'll say this is name is alloc test, and root source file is going to be testig. Boom. Or maybe we'll call it alloc test. Nice. Target is target, and optimize is optimize, which I think aren't here yet. Standard target options, and optimize is standard optimize option. Boom. And then we install artifact test.exe. Okay. So I think if we're just like alloc testig now, and we do main, we should get something here. Zig build. Let's see what it does. Oh, this thing needs to be B path. Little lazy path. Lazy path, that bad boy. Okay, cool. Okay, so what does our test look like? Uh, the real case that we're hitting this from. Why is there add executable and install artifact? Couldn't the first implicitly do the latter? You might do something like compile an executable to generate some code for me, right? Like, or like, do something as part of the build process, and then like you might say run that executable, and then as part of second build, and then like the second build is like your actual output, right? So you might have executables that you don't want to be like exposed to the install process at the end, but things that you might still want to build. So that's why they're separate. Okay, so the real problem that we have hit this, the inspiration for this is we have a database in another project we're using, or we're writing database, and this database has something that you're like reading from SQLite, and it's returning something of the form, DB results or something, is something of the form like ID with elements, and this element, I think, has another array inside it. I think we were counting stuff. So we were saying like key count or something. It was something like this. So we were doing something where we had a function where we were allocating this elements thing. Then we were allocating a hash map to count some sort of element. And there was some sort of nesting going on there. I don't think we have to get that complicated though. In reality, the problem here can be easily shown by a hash map and an array of string returns, I think. So we can say test function is going to return a array of strings, okay? This is what this thing wants to return. Okay, and so we get our scratch allocator. We say const my standard library is import stud, which means that we actually need to import this thing into this thing. Test exe root module add import stud from stud. Like this, I think. And then we can do, this guy is stud alloc scratch alloc. Okay. Maybe this thing just needs an allocator. Not sure. Okay, so here in our test function, we say, maybe we have like some sort of random number generator. So const stud is stud, and I think this is stud random, like this. And so let's say that we have like, we are doing something like allocating some number of strings. Sure, we can do that. Int range at most returns an evenly distributed random integer between these guys. Int range less than. It doesn't really matter. So we'll do like 0 to 100, right? We'll do up to 100 allocations. Holy shit, missed a lot of messages. First at birth, thanks for the prime. I just thought about adding something like this the other day to my data dependency checker for Python. Hell yeah. SQL database next project. That would be fun, but I've got other projects I want to do first. Sfuquel, yeah. Thanks for the inspiration. Good stuff in streams a lot. Thanks, man. Okay, so we'll say this is our return, and he's going to allocate maybe, num strings of this. Okay. And actually, it's easier if we use our little helper for like allocate this thing and then use it like an array, a growable array. So I think we have this guy. Runtime bounded array, initialize this with num strings. It's like this. Okay. And with our alloc. Boom. Okay. So this is our return. So at the end, we're going to return ret items. Boom. And in between here, I guess we're going to create some sort of hash map because that's kind of like the test case. Well, maybe there's something else we can do. I guess it doesn't really matter. Let's just say, let's pretend, we'll just say we allocated another thing. That's all we really need to do here. So like intermediate step is going to be another, let's just say that this is another intermediate alloc. We'll just say that we had some allocations to do in the middle, and we won't really think about what those entail. We'll just say, we'll okay, shut the fuck up. You don't have to come in here, spam for democracy and freedom in big caps. Just shut the fuck up, dude. It's so weird. Yeah, so we'll just pretend that this is like a hash map where you're counting things or something like that. Or grouping things in some way. And we'll just say that this is allocate, some use sizes of this much. Num intermediate alloc. Okay, oopsies. And then we'll say for 0 to num strings, ret I is like maybe stood format alloc print. Yeah, something like this. So we'll just print the number or something. Yeah. Okay, cool. Something like this. And then that means that we don't actually need this to be runtime bounded array. This can be back to alloc, like this. What was it? Num strings. Yeah. Okay, cool. This should work. This is an okay test. We need to make our, we need to make our scratch allocator and RNG. So this is stood random default prng. In it, we always in it with 0. And then we call test function with scratch and RNG random. Okay, we need the scratch allocator now. So this guy is gonna be like stood heap page allocator alloc. Let's just allocate like, I don't know, a meg or something. It doesn't really matter. Of U8s. We'll use this as our scratch buffer source. So we say var scratch is a scratch, a stud alloc scratch alloc initialized with this thing. Cool. And then this should work. So let's maybe print out what we get back. Like this. And then call it a day. Okay, give him a sec. He's thinking. He's mad because this guy needs to take a pointer. And this guy does not. Oopies. Forgot to write try somewhere. And I forgot to put an exclamation mark here to indicate this function can return an error. This guy can fail. True. Okay. Zig build and zig out bin test. Okay. So here we go. What the fuck is this? That doesn't look right. For ret string. Let's print the string. That seems a little nicer. With a new line. All right, there we go. 32 strings. 32 strings. And so what we should have here is allocation that looks kind of like return data, some sort of like intermediate scratch that we don't give a fuck about, and then our string storage, right? So if we were to look at like the memory address of the first string, so maybe we can do this, show me, I think that's how you do it. Yeah, so here are the addresses of all of our strings. You can see they're kind of just like sequential coming from our buffer, right? So like the first string comes at 48, 49, 4A, 4B, 4C, 4D. Every string is just like the next byte in our big initial buffer, right? And if we look at the value of the pointer itself that we got, like this, maybe we show it from ret to ret pointer to ret pointer plus ret len or something. This should show us kind of the memory range of the actual thing that we wanted to return. So we see that this thing, oh, what the fuck? Oh yeah, that's right. So this guy's in the range of from 9,000 to 9348. That doesn't sound right. Then this is at 9349, so there's actually no wasted memory, which is bad. Maybe this is just like, let's just write 1,000 in here. Hard code it. Something about this doesn't seem right. The whole is not a whole. Why not? So here we're seeing 2150, 2151. It means that there's no whole. Maybe this is not, is this not showing what I think it's showing? Ret pointer. Okay. Ret pointer. Let's just start there. Oh yeah, something, this is a weird, what the fuck is this showing? I don't understand. Okay, there's, can we do int from pointer, can we just like take this thing and make it a u size? Let's see if that kind of makes more sense. It might be that I don't understand the format here. Oh, I'm a dumbass, actually. It's because I didn't new line here. So I was just looking at part of this as well. Oops, okay. That makes more sense. Okay, so we have a guy going from, you know, A6000 to A6210, right? This is kind of like the list that we're returning. But then there's a big gap from 6210 to 8150, right? That's all of our wasted memory. And so the goal here is to make it so that all of this is like just bang sequential, that there's no gap. That's kind of the intent here. So the idea, I think, should be to just make a little double-ended allocator. So this scratch allocator is just kind of like a nice little, like a little wrapper around fixed buffer allocator, which is like a standard library type that takes a buffer and like basically just bumps the index forward, like we were saying earlier, right? We go, yo, here is buffer, pointer here, move pointer forward when allocate. Boom, 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 boom. So we're gonna have to like re-implement this functionality probably, which shouldn't be too bad. Should not be too bad, but it's why we have this type. So we don't really have much of a starting point. So I think maybe starting from scratch is reasonable. I also don't like the name scratch allocator. Why am I seeing a message from this band guy on top of the full screen video? Are you? That's kind of funny. Is it like broken? Was he doing some shit? I don't see anything. So I don't know. Maybe it fucked you in some way. I don't know. Try refreshing. Um. Okay. So I don't like the name Scratch Allocator because it's kind of more just like a linear allocator, right? That we happen to use as scratch space fairly often. For democracy and freedom with US flags, I'm watching from mobile phone, by the way. Dude, that's so fucking annoying. Yeah, there's nothing I can do about that. That's so fucking stupid. What a fucking loser. Um, and I guess really this is kind of like maybe more like a buffer allocator because it's not really linear. It's kind of like linear from both sides. Um, and so I guess what we're gonna have in here is we're gonna have some buffer that's backing storage, and we're gonna have end index or like left index and right index. And when you initialize this thing, I guess this is going to return a buffer allocator, and he's gonna maybe buff allocator just so I have to type less. uh, we take in a buffer and we store that thing. So we just go return. The left index is always 0 here. The right index is going to be buff len, I think, and buff is buff. Okay. So this means that we're gonna have to have this guy's gonna need to return like the allocator interface from the standard library, right? So let's take a quick look at what that is again. Alloc stood mem, I think it is allocator. Here we go. So this guy's got this v table that we need to implement. So we'll just copy paste that here. So I guess what we're gonna have. This is probably gonna be an allocator for the left side and right side, right? So I guess something like this maybe makes sense. We'll see. Well, I guess he's not going to be his own structure, right? We're gonna call like left allocator, and he's gonna return a stood mem allocator, right? That's what's gonna happen here. And this thing should be relatively easy. So I guess this means that we're going to have these functions in the vtable are going to be we need to like instantiate one of these, I guess, as like left vtable is going to be a stood mem allocator vtable, right? Like this with these functions defined. So we're going to be like here, let's just kind of whoop. So here we're going to implement these, and I guess we'll implement them all for the left side. I think we don't need to implement anything but alloc. Resize, we're just not going to handle. Remap, we're not going to handle. Free, we're not going to handle, right? All of these things are just like, remap doesn't exist. Resize, it's just like allocate a new blob. Free is like, we're just going to move the pointer back. We don't free individual elements. That was kind of the intent here. So all we need to implement is this guy. I guess we technically have to implement these guys, but we'll implement them as like null. So we'll call this like null resize. Like this. We'll call this null remap, and we'll call this null free. Okay? So null free does nothing. I guess this needs to be context here. And this is going to be alloc left. Simple. Okay. And this is return false, and this is return null. These guys don't do shit. Then our left vtable is just like, this is alloc left, this is null resize, this is null remap, and this is null free. Pipe. I guess we're kind of doing this. Okay. Alignment needs to come from stood mem here. Okay. Simple. And then we need to kind of discard all these parameters that we're not using. So, uh, word, 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 forward, 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 onwards and upwards. Boom, 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 boom. Okay, here we go. So alloc left. What does this guy do? He's going to do some sort of, we're gonna like look at the left index, right? And we're gonna return something that's like self buff from left index to something, right? Surely. I guess it's just the pointer. So it's like actually pointer plus self left index or something, right? That's probably the return value here, except for there's going to be some alignment problems, right? So we might have something where we have a buffer, we are pointing here, but like the thing that is allocated needs to be like in chunks of this size, right? So we need to bump the pointer forward before we do that allocation. So I think there's like stood mem align forward, easy, right? And so this is like round an address up to the next or current aligned address. So this is really fucking easy, right? Really easy. So we take a U8. Well, is this the type of the thing we're aligning forward? Yeah, so U size, I guess, makes sense here. And then we take the potential, like the lower bound of the address, and we're bumping it up to some alignment. Right, so probably just slap alignment in here, I would assume. I don't know if this takes alignments. It depends, no, because alignment has to be a T here. So T is a U size. So how do they do this in, what does alignment thing give us? Stood mem alignment. Forward, return the next address with this alignment. Oh, easy. We just do that instead. That's even nicer. So we go, give me the next thing of this alignment from lower bound. And this thing probably has to be U size, he said? Yeah, okay. So we need our pointer to self, which doesn't exist yet. So this is a buff allocator. Yep. And this is a pointer cast, a line cast of the context that we get back in here. And then we just say the lower bound is buff pointer plus left index int from pointer. That seems right. Right? So we take the left side of this buffer. I don't know what the pointer addition rules in this language are. I wouldn't be surprised if they're like C, where if pointer wasn't a U8, then this wouldn't be nice. So I think it's sometimes nicer to just think of these things as numbers. You know? This is kind of nicer to me. Because then I don't have to worry about all of the weird shit. I'm just gonna delete this message because I don't know what it means. So, but not gonna ban you or anything. Just use words that I can understand. Okay. So I assume this returns the new U size. Yep. So this is going to be return adder, and then I guess we need to move the left index. So this is going to be I guess it's like the end of this thing is going to be the address plus the length. Ret adder is, oh, this is like a debug tool that we don't need. So we can kind of do this, and then I guess the new left index. Hi, Lurk. Hi. Sup? So what's going on here? We take the ret end minus, I guess we'll call this like buff pointer is a U size, and then we can kind of do this here. Yeah. Then we don't need to do this. We can just call this buff pointer type. Then this is ret end minus buff pointer. Boom. Type. And then we can just return ret adder. Type. Okay, so where does this fall over? I guess we need to return that this allocation failed if this is out of bounds, right? So if ret end is greater than or equal to self buff len, we return null. right? Should be. I think that makes sense. And so now our left allocator, all it has to be is pointer is self type, and the v table is the left v table. Boom. I think this should be it. That should work. Now we don't have any like checkpointing or restore functionality, so we can't free any memory yet. But at the very least, we can test that allocating from this thing like gives us sequential addresses and gives us like things of the right size and stuff, right? So how would we do that? Left allocations. So let's make a little buffer to allocate from. We'll give them a little like 100 bytes, right? How do you do this? Like this. And we'll say we have a buff allocator initialized with this buffer, huge. Can we specify the alignment of this thing? Just to make this like super fucking clear what's happening. Otherwise, like the test might be inconsistent. Maybe like here. That seems like it's working. Okay. So buff alloc is this, and then if we want to do like buff alloc left allocator, we get this guy. I wonder if front and back are better names than left and right. Might be. Fix me front allocator, question mark. And so we do a little. So if we try to allocate 101 bytes, this should fail. Expect error, error out of memory. If we try to do this, right? We should expect this to work. And I guess we're kind of expecting this to be the base address of buffer, right? We're kind of expecting this. If we try to allocate from this guy from the start, we should get the start, right? Let's kind of put this like this, or we can kind of do this. We can just reassign him down here just to reset him because we don't have reset capability, or we can just add it. Let's do that. Let's do that. So this guy takes in himself, and all we have to do here is we say left index is equal to 0, and right index is the buffer. But what we should do also, in like Zig fashion, is kind of clear out that memory that we used to kind of flag memory issues later, right? So what we can do is we can do memset from 0 to left index as undefined. And then we can memset from right index to onwards. We can set this undefined. But right index might be this might be wrong, so we have to say if self right index is less than self buffline. I think that this won't work otherwise. There we go. Cool. Okay, so we should go back here. And what do we want to do now? Maybe allocate some like we can try to do some like intermediate allocations. So let's do like allocate like, I don't know, 4 I32s. We expect these to come from the beginning of the buffer, and then if we expect this to be like plus 16 would be the next allocations pointer. I guess we need to look at the pointer in all these. Sure. That's probably good enough. If this works. We need to actually have a way to run these tests. uh, test exe, add test. Which is gonna be name alloc test. Like this. And then I think the parameters are all kind of just the same here. Copy paste. Okay, and then let's just install this test. Fuck it. Okay. For now. Okay, he's pissed. What's he pissed about? Expected type this, found usize. True. True. So we were working in usizes, but we need to pointer from int this guy. Convert him into the pointer that he wants to be. Okay, error union is ignored on all these tests. True. Okay. This does not support field access. True. We do need to write try on these guys. Like this. Boom. Boom. Incompatible pointer types. Align for this thing and pointer 532. True. Can we just call this like buff start is a usize int from pointer of buff. Then we could do I don't know what. Buff start here. Buff start here. Buff start plus 16. And then can we just do like, or maybe it makes sense to do this. Pointer as slice pointer base usize. Is we take in, you know, slice of any type and we return a usize and we just do like base is pointer from or return int from pointer as pointer. Boom. Which means that now I can go like this. Slice pointer base usize. Huge. Like this. Okay. Is he happy now? Close. Alright, let's zig build. Please God. Okay. Alloc test. Test allocations is failing. 272 is returning out of memory on when we try to alloc 100 bytes. Ooh, interesting. Interesting. I did not expect this to fail, because we should have enough space for that, right? So what the fuck is the problem? What is the problem? Let's take a peek. Let's take a peek. Can we breakpoint here and just kind of step in and see what's happening? Okay. I want to get into where the fuck we are. Where the fuck are we? Oh, here we go. Alloc left. Okay. So we have buff pointer. Sure, that's a number. Right now, our left index is 0, as expected. Ret adder is this, which is the same as the buffer pointer. Okay. Oh. Greater than or equal to? Good thing we wrote that test. This should be like this. Zig build. Alloc test. Still failing, huh? Is it from the same spot? Yes. Interesting. Was not expecting that. Can we just do this? Are we in our thing? No. Oh, it's we can't breakpoint on just like the error. Fuck off. I guess it's maybe we can do something like unreachable here. And then GDB will like crash when that happens, and then we can take a look. A little easier. Nice. Oh, except it's supposed to the first time. Fuck. Everything's so hard. Everything's so hard. I guess we just spam step a little bit. Fine. Okay. So, p ret end. P ret end minus buff pointer. 100. P, okay, so great. So this shouldn't happen. No? If ret end is greater than that? Oh. I'm a dumbass again? This is a... we need to be doing this. Const buff end is buff pointer plus self buff len. Then we compare ret end to buff end. Oopsies. Because we were comparing, like, the pointer, the address of the thing, with, like, 100. And of fucking course, that doesn't work. I guess we could also do it this way. No, we can't. Okay, there we go. Now? Maybe? Good thing we wrote tests. All one test paths, baby! Hell yeah. Hell yeah. Okay. So now we theoretically have something that can allocate from the left, which is hype. And now, left allocator, and now we just need to make one for the right side as well, which should be relatively straightforward, right? So, this is our right allocator. And this is the right vtable, which is just the same as the left vtable with an alloc right in there. Pipe. And alloc right surely is going to look a little bit like alloc left. So surely we're going to still get ourselves. Surely we still want the buffer pointer and the buffer end. These are all the same. These are all the same. The lower bound, though, probably doesn't matter. Upper bound is what we care about now. And it's going to be buff end minus right index, right? Let's think about this for a second. I think maybe a -1. Right? Because right index is equal to the length. If we were to return len, like a len pointer, right? This is out of bounds. So the first thing that we could return is this -1. Or we can just set the right index to here. Uh-huh. And I'm just going to put a fix me down here because I know that this is going to be a problem. Fix me test collision of left and right allocators. Because I know that the way that we wrote the left allocator right now, he doesn't take into account the right index at all on alloc left, and he needs to, right? This ret end is like buff end test here. This is wrong. This is wrong. This should be probably with like minus right side or something, but we'll tackle that later. Okay, so we've got like the upper bound here. So I guess we're going to go backward now from this alignment. And then we need to subtract the length. But the length, we subtract the length first. We subtract the length first. Because if you have something that's like say you want to be aligned in like increments of like this much or something, right? I think it's like totally valid for you to return an array that starts here but ends here, right? Where like the end doesn't have to be aligned, only the start has to be aligned, I think. So we need to make sure that we're trying to align the start, not the end. So we subtract the length of the thing from the right side because the allocation needs to go forwards in memory. I think that makes sense. Uh, okay. Then the failure condition is that like ret adder is like greater is like less than left index. I think that's the failure case. If it's equal, because I think left index is where the next allocation will come from. So I think that's okay. I think. Yeah. Okay, yeah, that makes sense. Then we decrement right index. So right index just becomes ret adder minus 1. Right? Because we want this to be the first thing we can allocate from. Is what we said before. Which I think is fine. I think that's fine. Okay. So let's write some tests for the right allocator. Okay, so let's make this aligned. This needs to be a multiple of 4, which this is, okay? So here we want to get the right allocator, and I think we want to test that 100 is okay, 101 is not okay, reset this guy. I want to make sure that like if we can allocate 1 byte, that this becomes like buff start plus 99. If we did like 1 U8, you know? Zig build. He got mad because I said left view table here again. Type. Okay, so he's pissed off immediately. We done fucked something up. That's kind of fun. What did we do wrong? Allocate. So we take. I guess we just run this guy with GDB and take a look, huh? Jesus Christ, we've done fucked up hard. He is angry, my man. That's funny. Can we just breakpoint here? We did it again. We did it again. This is left index is 0. Ret address is a fucking pointer. So if this is buff pointer plus this, we did it again. The same fucking bug. We wrote it twice. Okay, wait. Does that work? No, because trying to allocate 100 bytes is failing because ret address is somehow less than this? That's pretty surprising. So let's think about this. We have right index as the first number that we can return. Okay? We subtract that from here. Yeah, wait, what the fuck are we doing here? This should be buff start plus this. Because the right index is not like a number from 0 to 100, which maybe it could be. Maybe that works better. Ah, whatever. Okay. I think this is still wrong, actually, when I look at this, because length is going to be like 1. Right? So here, right index, I think, should actually be buff len, not buff len minus 1, like we were saying before, because the subtraction of length there is going to offset that thing. The length of the allocation that they're asking for, right? Because this is never going to be 0. That seems reasonable to me. So we do buff pointer plus the right index minus length. And right index is now just ret address. Yeah. Yeah. Okay, so that's working so far. Hype. So let's see. What other things we want to try? So we want to try allocating a I32 here now. And what we're expecting here is that, let's draw it out. We're expecting that we have alignment here, 4 bytes away from the end, but we've kind of used up this space, right? So we're kind of expecting that this is going to have to go back all the way to here to allocate the next thing, right? So we're expecting this to be plus 92, I think. Ooh, he's mad. That's interesting. Very interesting. Why? Why? What's he pissed about? Okay, backtrace is not fucked up, which is huge for us. So his mem set is mad. Okay. Because of this? He's going, that page is not mapped or something? Why not? I guess we're gonna have to breakpoint here. And figure it out. Step, 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 step. Until we see something that looks like us. Here we go. Okay. Okay, so we have right index. That would do it, huh? God damn it, dude. Ret adder minus buff pointer. Dude, we've written the same bug on both sides multiple times. That's so funny. Fuck. Okay, it works now. And then I guess, like, is there anything else I really want to test here? I think just like collision. We can kind of play it fast and lose. Allocator collision. So let's get the right allocator into some state. So let's maybe try to allocate 50 bytes or something. So right index should be at 50, right? So we're kind of hoping. Maybe we'll do 25 on each side. That seems right to me. So left at 25. And so we should be able to like checkpoint here. Okay, which we don't have implemented yet, but we will do that in a second. And then we should be able to do like right allocate 50. This should succeed. And should be at 25. This should like push all the way to the left so that we're like at the position 25 here. So this should be like the very, we should be able to test this. Stood testing expect equal buff start plus 25 should be what we get here. Okay. Then if we were to restore the checkpoint, and do this again. But with 51, this should fail. Yep. That's huge for us. And so we just need to implement checkpoint and restore, which should be easy, right? This is just like a little left and right? We just kind of write these guys down. Checkpoint takes in our buff allocator and returns a checkpoint. And it's just like return, easy. Left index is left index. Wow, we're getting crazy out here. And right is right. Right? Right is right, right? And then on restore, I guess this stuff shouldn't be between the two allocators. We take in our little allocator, we take in our checkpoint, and it's almost as simple as doing self left index is equal left index, right? And right is right. But it's not quite that simple because we want to clear out as much as we can. What is this piss about? Hello? Oh, because this is a restore point. Because it's a name colliding here. Oopsies. Okay, so we also want to do this like memset shit. So this is from the restore point should be further to the left. So it should be like this, and like the restore point right index should be to the right of the existing right index, right? Because we're assuming that we're restoring like backwards, like we're creating more space by restoring, not the other way around. Okay. And then here we do the same test with the left, right? So we go the same thing, but with left allocator here. Like this. Left alloc. And I think that should work. He's mad? Why? Compilation errors. Hello? Is it from this or from the checkpoint stuff? Oh, oops. On expect error, we can't use this thing that returns a U size. Oopsies. Oopies. We can't even write try. We're like, please just like check that this thing is an error, sir. There we go. Hi. Thanks for the tier 1, McBabo. Much appreciated. Okay, so interestingly, this fails. Oh, because we didn't fucking fix the left allocator side. Right. That's the whole point of this, is that it's fucking broken. I forgot. So this is at 194 on the left alloc. Yep. So on left, we just need to make sure that we are checking that the right end, this should be this. The end is from the right index, and we just compare with that. Should be. All 3 tests pass. Let's go, baby! Let's go! So we should be able to just now apply apply to test case. Right? So we need to make sure that this thing that we wrote is like a sane, helpful thing, right? So instead of using our boring scratch allocator, boring buff allocator, baby. Same shit. And what we're hoping now is that when we run test function, we have like, what would be nice is if we could get a linear allocator out of this guy. Right? So what would be kind of sick is if we had like return alloc here, and then like scratch as a linear alloc, right? And then what we could do is we could checkpoint and restore the linear allocator based off of what we're seeing here, right? So we could go like checkpoint is scratch checkpoint, and then we could do defer restore scratch scratch restore checkpoint here. And then we could just kind of do whatever the fuck we want on this scratch allocator here, right? We use the scratch allocator here, right? That seems kind of slick. Kind of slick. So, and then what would be nice there is that we can choose from like the caller of this thing. We can say, okay, do your return on the left side and your scratch allocations on the right side. That would be kind of slick. That would be kind of slick. So the problem here is that this linear allocator would have to support both the right side and left side. Oh my god, we have so many fucking bullshit people today. Ban, fuck off. Do you edit your VODs on Linux? I don't edit them. The ultimate fix. Chris, thanks for the prime. The most I do is like clip them with FFmpeg, which is like super straightforward. I have like zero interest in video editing. So it is what it is. I realized at some point I wrote that video editor a while back. Let's see if we can find it. The idea was supposed to be something that helped me like cut down VODs into like something more like snappy, like 20-minute videos. But then I realized that no matter what, the amount of time that took was like more time than like writing the code. And so I didn't do it anymore. But I did write this like kind of slick video editor. Excuse me, I would like to skip this ad, please. God. Okay. Do we have like a little demo of it somewhere in here? Yeah, look at this guy. Look at this guy. So it like automatically like transcribed the whole video, and then you could like select chunks from the timeline on here that had like audio waveforms. It was kind of slick. Yeah, like kind of like this. So you would like select areas, and then you could like export that whole thing, I think. But I never ended up using it because it's just too much work. Too much work. Okay, linear allocator. Realize it's not good enough. And now we're like, linear allocator interface. So I think that because the left and right side are different implementations, I think that we need like linear allocator is like a thing that has a runtime vtable, I think. So this is going to be like vtable is a struct, and this linear allocator interface is going to have a checkpoint, which is going to be something. A pointer to a function that takes in literally just like our context, I think. Why is this thing mad at me? Hello? This should be fine. I don't understand why this is erroring. Expected return expression. Oh, I see. Oof. What is the checkpoint type? usize, I guess. Um, then we're gonna have restore that takes in the usize. And then we're gonna have allocator, which which takes in our context and returns a stood mem allocator. I think this is like the linear allocator interface, I think. We'll see if this plays out the way I expect it to, but you never know. So this guy's gonna be like, I have this and a this, right? I have some functions that I can call as well as a context. So it's almost like now we need like left linear. Returns a linear allocator. And this is going to return self, and he's going to say return left linear vtable. Weird. Weird. But we'll see how this plays out. And then we have like right linear as well. It's going to do the same shit. I expect that this kind of is easy to implement. Right? Because like the checkpoint and restore is just going to be like use the left and right indexes. And then the allocator is like a function that we already have. Right? So let's take a look at that. Left linear is linear allocator vtable, okay, who has checkpoint is equal to left checkpoint. You know, restore is left restore. And what was the other thing? Allocator is equal to left allocator. I think that this is going to get mad. Context, I guess we'll call it. So left allocator context. This is easy. This takes in context as an any opaque and returns a stood mem allocator, which just casts this to our self pointer, which is a buff allocator. Like this. Boom. Okay. And then we just call like self left allocator. Boom. Left checkpoint is, what is the return? A usize? And this is just like return self left index. And left restore is just like the left half of existing restore, right? So it's almost like restore should be like left restore, something like this, so that we can reuse this in the context thing. Yeah. And then this part is left, and this part is right. And so then this stuff comes down here into left restore, but now left restore takes in a context instead of self. So this is left restore context. This is left restore. So all of these guys need left restore context here. Left restore takes in self correctly. This is all making sense. This is all looking great, dude. And this is just like left restore, left index. Boom. Boom. Boom, boom, boom. Easy. Okay, so then the right side is all the same. Right, so we're just gonna do like a little copy pasties of this and just replace the word left with right. I think that's it. I guess this right restore needs to be implemented correctly. Right restore has to be implemented like this. Cool. Left. Why does this not work? Oh, this should be left linear v table, and then this should be right linear v table. Where the fuck that was. Okay. That's like a maybe. Undeclared use of identifier linear alloc. Oh. Yeah, we did call this something else, huh? Okay. So now test function, when we call this thing, his return allocator is scratch left allocator, and right is, or the scratch is scratch right linear. That seems kind of nice. Then the stuff that we're returning comes off the return alloc in here. Okay. It's true, this should not be a pointer. This should be a concrete type. No field pointer and linear allocator. True. We called it context. Boom. Boom. I like that word better. Okay, so then we have to make it so that these functions actually have nice functions to call, right? So we have checkpoint that takes in self, which is a linear allocator, and returns a usize, and it just calls self vtable checkpoint with our context. We have restore is the same, but he's taking in the usize this time. And we have allocator, which returns the stood mem allocator. And this is just allocator. Boom. Simple. Does that work? Close. These guys need to be const pointers because these are not modifiable. And let's see if that fixes our problem. So what we're hoping to see here, I guess, is that the addresses for the slice of memory that we returned at the beginning, plus all of the content of the strings that we have in those, we want those to be all sequential, right? That was the original problem, right? Just to remind ourselves, it was that we had, slice of memory of stuff that we want to return. Then we had, intermediate allocations that were kind of like internal implementation details that we didn't want to return. Then like string content that was referenced by this array, right? And what we're hoping is that now this whole block has moved to the bottom and that these guys are contiguous in the return. And it looks like we have seen this, right? So we're seeing that this allocation goes from 9C000 to 9C210, and then the first thing that we get back is at 9C210. Fuck yeah, dude. Looking pretty good. I'm happy with that. Yeah, I think this solves a lot of my problems, to be honest. I think this is just like relatively straightforward implementation. Very slight improvement over the existing Scratch allocator, but I think that this this will reduce so much mental overhead in the future. It'll be so easy to be like, you could even extend this like a little further. To be honest, you could do something like if you're trying to say like, if you have a function that's like return some list of unknown size, right? And you could take in like ret alloc as a linear allocator now, and scratch as another linear allocator. So these could kind of be like the left and right side. And if you wanted to do something like read into a file in the left allocator, you could do something like as crazy as you could start getting like ret alloc, alloc half space or something, like, or alloc a lot, right? Like to get like half the size of the available allocator or something, right? So that you can like bisect this, and then you could like read into this thing and then like truncate it, based off some heuristic. And you don't have to worry about like running out of space or anything, or like interleaving allocations, because now you can just say anything from the scratch comes with a scratch linear allocator. That's pretty sick. Pretty sick. I think this is gonna like simplify mental overhead a lot, which is already kind of nice because we've already simplified mental overhead a lot by having the scratch allocator in the first place. So the farther we get down this path, the less we have to think about allocations in general, which is hype. It's hype. Simple. All right, cool. I'm happy with that. Twitch viewers, stick around. We're gonna pivot into a second segment. YouTube though, thanks for watching. If you like what you saw, we stream most days at 12:30 to 4 o'clock Pacific time. Swing by if you want. Please consider supporting the stream. We have segments of the stream that don't go up on YouTube. They go to Patreon, YouTube members, or in Twitch VODs. If you want to see those, the stream will end someday when we run out of money, right? And so every dollar I make kind of extends the lifetime of this by some amount. So if you want to keep seeing more stuff from me, please consider contributing in some way, but obviously no pressure and no worries if that is not something that you want to do. Yeah, YouTube, peace out, and Twitch, let's pivot to the next segment.